new people don't come to class early for whatever reason, I guess I have to start doing something about it. Okay, so let's continue the discussion from the previous lecture, and hopefully we'll be done by the orbit equation today. So we started talking about elliptical orbits, right? Pardon me? Yeah, that's right. That's what we did, right? That's what we talked about. And so let's start with an ellipse and see how we deal with an elliptical orbit, the nomenclature and whatever. We are going to have 2 points, focus points, where your mass M1 is located at, and there's another point, empty focus, which is the focus of an ellipse, but there's no mass there. Point P is the periapsis that is located on the apse line. Right. We already know that this distance is called RP, and this distance is going to be called RA. That's the distance from the furthest point on the orbit. And then point A is called apoapsis. This length is called, we usually use A for it, it's called the semi-major axis. This distance, use B for it, it's called the semi-minor axis. This R of B is the R at point B, just above the center of your ellipse. Angle at that point is called angle beta. Okay, these are all the things that we need to know before talking about the orbit equations. Going into the ellipse, this is how we talk about everything in an elliptical orbit. And what was the orbit equation? Who can tell me from the top of their head? H squared divided by mu. What else? Cosine of theta, right? This was the general orbit equation. So based on this orbit equation, how can we calculate R of A? What is theta here? pi, exactly. So theta 180 degrees, which means that cosine of theta is -1, right? So R of A is going to be H squared divided by mu, 1 minus 1 divided by 1 minus E. And we already know how to calculate R of P, right? Theta 0, cosine of theta 1, which means that R of P is going to be equal to H squared divided by mu, 1, right? How can we find the length of semi-major axis? A. What do you think that is? Let's talk about it in terms of RA and RP, right? It is not RA minus RP. This is this length, right? RA minus RP is, we'll talk about RA minus RP. But it's essentially RA plus RP divided by 2, right? That's it. So if you plug in these equations, the equations we have, you're going to get h squared divided by 2 mu, right? 1 over 1 minus e, right? Is it clear? Which essentially means that we can calculate this using this equation. Right? The denominator is going to be 1 minus e squared, and there's no 2 here. I'm pretty sure you know how to get from here to the other equation. Multiply the denominators. 1 plus e multiplied by 1 minus e is going to be 1 minus e squared. Then the numerator here, we have to have 1 minus e plus 1 plus e. Right? E's cancel out. You're going to end up with a 2. These 2 here will cancel out this 2, and you'll end up with this equation, right? For the semi-major axis. Which means that we can have the orbit equation as a function of your semi-major axis and the eccentricity vector, 1 minus e squared plus 1 plus e cosine of theta. So the new orbit equation as a function of semi-major axis. So what is RP using this equation? Just plug in the value of 0 for theta, right? You're going to get a multiplied by 1 minus e squared divided by 1 plus e. So what will we end up with? One minus e squared is 1 plus e multiplied by 1 minus e, right? We're going to have 1 plus e in the denominator, 1 plus e in the numerator. They will cancel out. A multiplied by 1 minus e. There is no squared anymore, right? Right? What about RA? RA. Okay. Just a plus, right? So how can we find this RB here? Using that orbit equation. R of B. This is the RB, right? The only thing we really need to do is to plug in beta for your theta. So R of B is going to be A multiplied by 1 minus E squared divided by 1 plus E cosine of beta. Are we moving too fast? No, just simple equations. So I don't want to spend that much time on them. What is this length? FC. How can we calculate it? It is not always that. No. We didn't say that this is half. This is the half point between these two. Oh, A minus RP, right? A, this is the semi-major axis minus RP, right? Yes? Okay. So A minus RP, right? This is also the projection of this RB on this axis, right? On the major axis. So we can actually say it is also equals to RB. Let me ask you this. Let me just bring you in. So this length is also the projection of this RB on this axis, right? How can we calculate this projection? Cosine of beta RB, right? But that is not the angle in this axis. This is the angle, right? So how can we find this angle? That's it. So RB cosine pi minus or 180. We usually do 180 degrees. 1 minus beta. What is cosine of 180 minus beta? Does anyone remember from the trig relationships? It is minus cosine of beta, right? Right? So you'll end up with minus RB cosine of beta. Okay. Next, actually, there are some interesting things that happen here when it comes to these calculations. Let's talk about this a little further. A minus RP. What is the equation for RP? Right. So N A minus A 1 minus E, right? Which is A minus plus AE, right? Cancel them out. Which means that this length FC is actually equal to your semi-major axis multiplied by eccentricity, right? Okay. Which means that this negative RB cosine of beta is also equals to AE, right? Because FC is equals to AE, and we have two equations for FC, right? We also have an equation here for RB, A 1 minus A squared divided by 1E plus cosine of beta. And if you play with that equation, you'll end up with this interesting relationship that E, let's actually clean this. E is equals to negative cosine of beta. So your eccentricity vector is equals to negative cosine of this angle. Beta is the angle that and it is the true anomaly at which you are on the center, like on the center line. So when you're at the center line, if you know that true anomaly, you can calculate the eccentricity of the orbit, right? Okay. So let's say we have found that equation, and let's say we plug that in here. So cosine of beta is negative e, right? We're going to have 1 minus e squared, 1 minus e squared, means that they will cancel out, right? And we can conclude that RB is equals to your semi-major axis, that length. But the semi-minor axis, this one, B, and there's no but, I mean, for the calculations of semi-minor axis, let me ask you, how can we calculate the length of the semi-minor axis B, a small b? Negative a sine theta. How did you get there?
Beta.
Oh, beta.
Well, we know RB is A now, and we use the same negative cosine theta relationship below to find the theta, so it becomes negative sine theta.
So what Igor is telling us is that B is actually equal to RB, the projection of RB on the minor axis, the center line, right? Which is going to be RB sine of pi minus, or 180 minus beta. What is the sine of 180 minus beta? So let me ask you this. Which quadrant do we have this 180 minus beta? In which quadrant that is? That's the second quadrant, right? Is sine negative or positive in that second quadrant? It is positive. Sine is positive, right? Okay. So it cannot be negative sine of beta, right? We can answer that with another question. What is sine of 30 degrees? Sine of 30 degrees. I think we have one answer here. No. That's sine of 45 degrees. And sine of 60 degrees is root 3 over 2, right? Which means that sine of 30, you can actually use your phones. That doesn't really matter. I don't really care. No, I mean, it is not disappointing. Sine of 30. 1/2. Okay. What is sine of 180 minus 30? So sine of 150 degrees, right? Let's see. It's the same thing, right? 1/2, right? Which means that B is going to be equal to RB sine of beta. Okay. But we had a relationship here that helped us calculate the sine of beta as it relates to eccentricity, but we don't cosine of beta as it relates to eccentricity, but we don't have that relationship for sine of beta. So that's one way you can find that relationship, but we can also use the Pythagoras theorem, right? RB squared is equals to AE, A multiplied by the eccentricity squared plus B squared, right? You can also use that as well, which means that your B is going to be equal to the square root of RB, which is A squared minus a squared e squared, right? You can take the a out. Your b is equals to 1 minus e squared. Okay. So we have the semi-major axis. We have the semi-minor axis. We have all of the relationships we need. We actually didn't need to derive all of these equations, because as long as you have this orbit equation and you know the naming schemes here, you should be able to find all of those. These are just simple mathematical relationships. But one thing we need to prove is that this orbit is an elliptical orbit. Okay? We just accepted the fact that if your eccentricity is between 0 and 1, your orbit is an elliptical orbit, right? Well, how can we? Yes.
In the case of the concentric orbit, which is still an elliptical orbit, right?
It's a special case of an elliptical orbit, right?
You don't have two foci. Does it matter? Because theta is going to be -1.
What do you mean by does it matter? Does it matter for what? It's a different orbit. We have the orbit equation. We find whatever we need from there, right? So we only have one focus.
So like FC doesn't matter and stuff like that.
That's 0, right? Yes, just the radius, right? Okay. Well, how can we prove? And let's think about it. How can we prove that this is an elliptical orbit? When it came to the circular orbit, we just found out that your r is constant, right? Which means that you're dealing with a circle, right? How can we prove that this is an elliptical orbit and not a weirded shape of orbit, right? Here.
This is the thing with the area as time continues.
How would you prove that this is an elliptical orbit using that? I mean, I'm not saying you couldn't, but I'm just asking whether you can elaborate on that. Let me ask you another question. What is the equation of an ellipse as a function of x and y? Like x.
Like 1/2 x squared plus 1/2 y squared, just like a coefficient of subtraction.
1/2 x squared plus 1/2 y squared.
Yeah, I think there's like a fraction coefficient in front of the x's and the y's, and the x's are squared.
You're moving in the right direction.
And it equals like 2 or something instead of 0.
You're moving in the right direction, but it's not the right final answer.
Isn't it just 1 over x squared plus 1 over y squared equals something?
So it is an equation of a circle was this, right? If this was the radius of the circle, right? When you're dealing with an ellipse, you have a length a, you have a length b, right? It's not a constant a anymore. So an ellipse is going to be x divided by a squared plus y divided by b squared. This is equals to 1, right? This is the equation for an ellipse. In orbital mechanics, the mathematics are not that hard. Like you don't have partial differential equations, but these are you will see a lot of these different things, right? So you have to make sure your mind is fresh. You don't have to memorize them, but you just have to make sure your mind is fresh. Okay, so to prove that this is an elliptical orbit, we have to prove that this holds true, right? So the first step for us is to find the x. Okay, your x here, let's say this is, let me actually use another elliptical orbit like this, x. x, y, right? X and y start from the center. And this is your r with angle theta, right? How can we find x? X is going to be the projection of this on this axis plus this length, right? That will be your x. So AE plus r cosine of theta. And what about y? Y is going to be equals to r sine of theta, right? That's it. Okay. So y, r sine of theta. And let's use these two to see what we can get. X, AE plus, what was the orbital equation as a function of the semi-major axis? A, 1 minus E squared divided by 1 plus E cosine of theta, cosine of theta. Right? We can actually combine these two terms to get to this. AE plus AE squared cosine of theta plus A cosine of theta minus AE squared cosine of theta divided by 1 plus E cosine of theta. Okay, these two will cancel out, and we are going to end up with this. X is equals to A E plus cosine of theta divided by 1 plus E cosine of theta, right? This will be your X. For Y, your Y, we have R sine of theta. So Y is going to be equals to A 1 minus E squared divided by 1 plus E cosine of theta sine of theta, which means that you are going to have A sine of theta minus A E sine of theta divided by 1 plus E cosine of theta. Okay? And we are looking for x divided by A and y divided by B. So let's actually make that division. Let's actually do this. We have x here. Let me bring x. X divided by A is going to be equal to whatever we have over there. That's E plus cosine of theta, right? Let me just make sure I'm moving in the correct. Yes. And what can we do for y divided by b? There is no b present there. What can we do about that? What can we do about that? Let's go back to this equation here. Huh?
Factor out a sine beta and make that b.
A sine beta.
On the top.
A sine beta?
Yeah.
But A sine beta is not B. Is it? Oh, yeah. Why don't we use this?
I guess you could.
I mean, it should result in the same thing, right?
Yeah.
Let's see. Do we want to take another route? Aha. Let's actually talk about this. This is interesting to me. What would be the difference between using this formulation for B and this one, right? RB is equals to A, right? What would be the difference there?
Well, you would still have a function of theta if you use the rounded arm. Like a change as you go around.
We will still have a function of, well, we will still have a function of theta if we choose the one on top as well, right? You said theta, right? Okay. So that doesn't really affect theta that much. But we are going to introduce a new parameter beta there, right? And we don't want to do that, right? Because we already have E and theta here. We want to keep it to E and theta, right? So it is better to use the second one. Does it make sense? Okay. So eventually y divided by b is going to be equals to a square root of 1 minus e squared divided by 1 plus e cosine of theta. And what we did is multiply by sine of theta. And what we did was that we said a is equals to b divided by the square root of 1 minus e squared. Substitute that in here. 1 square root of 1 minus e squared will cancel out with this, and you will get a square root of 1 minus e squared on the numerator. Okay. So what is the next step? The next step is to put them in this equation, right? Okay. So let's do that, and let's see what we are going to get. We have e plus cosine of theta squared, e plus cosine of theta divided by 1 plus e cosine of theta squared. This is right, plus a square root of 1 minus e squared sine of theta divided by 1 plus e cosine of theta. And we want to see if this is equals to 1, right? That's the idea here, based on this equation. Okay, this is also a square. So e squared plus 2e cosine of theta plus cosine of theta squared. This is all numerator. Then this part is going to be 1 minus e squared sine squared theta, right? And all of this is divided by 1 plus e cosine of theta. Is this true? Does make sense. Let's see if we can make any simplifications. Okay, e squared, let me write it down here. Cosine of theta plus sine squared theta minus e squared sine squared theta. And there's also a cosine squared somewhere. Yeah, cosine squared. How can I simplify this further? sine squared plus cosine squared is 1. Okay? That is true. So we're going to end up with a 1. What else? Look at the denominator. We want to end up with something like this. That's squared, right? We want to end up with something like this. So what can we say about sine squared by itself? How can we change it to cosine? It's going to be 1 minus cosine squared, right? So e squared plus 1 minus e squared, 1 minus cosine squared for this, plus 2e, there's an e here, right? Yes. There is an 2e cosine of theta divided by this, right? And so we are going to end up with an e squared, negative e squared, which will cancel out with this, right? And positive e squared cosine squared. So let me remove this. Let me mark this. We're going to end up with 1 plus e squared cosine squared plus 2e cosine of theta, right? What can we replace this with? 1 plus e cosine of theta squared, right? That's the expansion of the denominator. So 1 plus e cosine of theta squared divided by 1 plus e cosine of theta squared, right? Is it clear? Did you guys follow? And it is equals to 1. So we have proven this is an elliptical orbit, right? So if you're what's up?
This is quite the derivation.
Yeah, I was getting lost at the bit, and I didn't have it on my notes, so I had to derive it myself. Yeah. Okay. So let's talk about the specific energy of the orbit. The specific energy of this orbit is also negative. The same is true for a circular orbit. And we can find the specific energy of this orbit using this equation. This is an equation we saw earlier when we were dealing with when we were finding the orbit equations, right? 1 minus e squared. There's also a negative sign, all right?
How do you determine elliptical obviously 1? Is that b equals 1? Is that why it's short?
No. When this is equals 1, this essentially means that this equation is equals to 1, which is an equation of that ellipse.
So how do you know that it's a fraction squared? No, it's equal to 1, but what about that over a squared plus y over b squared?
That's the equation for an ellipse from your mathematics.
But was there a way that we found that out from this problem?
No,
Just simple?
I didn't assume it. It is already proven, but it is out of we didn't prove it here. I'm pretty sure you can find a proof for this equation somewhere. I'm pretty sure you have already seen the equation for a circle is this, right? That's an equation for a circle, right? This is also an equation for an ellipse. This is, I'm not sure if you have seen the proof in your earlier mathematics courses or in your high school, but if you search for the proof, it is out there. Okay? But we just thought it is given to us. Okay. Yeah, a specific energy of an ellipse. We also know that H is equals to mu A, 1 minus E squared. You can actually calculate that by just accept that from me. And this eventually means that your epsilon is negative mu divided by 2a, which also means that the energy balance here is going to be your kinetic energy, V squared divided by 2 minus mu r is equals to negative mu a, right? We talked about this energy balance, this energy equation, which is also called the living force equation, right? You remember, hopefully you remember this from the previous lectures. Epsilon is equals to V squared divided by 2 mu r, right? And we said epsilon is a constant value. We found the epsilon p. This equation is called the living force equation, based on the French phrase vis-a-vis, something like that. I don't remember. A lot of equations on this board. That's orbital mechanics for you. Okay. We can also find the orbits, the time it takes, a period, the time it takes to get a full orbit using these two equations, 2 pi divided by mu squared h square root of 1 minus e squared to the cubed. Playing with that equation a little bit, we can actually get it in terms of a, 2 pi divided by the square root of mu a 3 by 2. Okay. Period of an elliptical orbit. Mu squared, not mu. Mu squared. Let me clean these parts of the board and give you the final equation for elliptical orbits. We can find Rp divided by Ra as 1 minus E divided by 1 plus E. But these are the things that you can calculate, which essentially means that we can actually find E as only a function of Rp and Ra. Ra minus Rp divided by Ra plus Rp. So, what is Ra minus Rp? Not Fc, no. This is this length minus this length.
I know you said this wasn't right earlier about the semi-major axis.
No. Think about it this way. Rp is also this length, right? These are the same length. So what will happen if you remove this part of Ra? What is the length you are getting? Exactly. Distance between these two foci, right? Let's say focal distance, whatever you want to call it. Distance between the two foci. Okay? What is Ra plus Rp? 2a, right? That's twice the size of semi-major axis, or we can call it major axis. So your eccentricity vector of an elliptical orbit does not depend on the semi-minor axis. All right? What does this mean? This means that, let's say you have this orbit, or this orbit, or this orbit. All of these will have the same eccentricity vector. Right? We can also have something called a rectilinear elliptical orbit, that it moves on a line, right, like this. But that's all of the scope of this course. And or a rectilinear ellipse. Well, one last equation, and we'll be done. The average distance or average R during an elliptical orbit. What is the average R in a circular orbit? Average R in a circular orbit. R, right? So here, we are interested in finding the average R in an elliptical orbit, which can be calculated by 1 over 2 pi a 1 minus e squared 2 pi 1 minus e squared. We can simplify this to a square root of 1 minus e squared. This is how you can find the average distance. This also means that we can find the average distance as the square root of RP and on RA. Let's move on to the parabolic trajectories and hyperbolic trajectories, and then we'll come back and solve an example from elliptical orbits. Okay.
Where does this average R generally appear? Is it closer to B or closer to A?
I didn't hear. Can you repeat the question?
You said average R. Is it closer to B or closer to A from the focal, or not from the focal, from the origin?
Average R, is it? Are you talking about this length or the location that happens?
Yeah, like location.
You have to calculate it in a minute, so give it some time. Okay, let's talk about the parabolic and hyperbolic trajectories very quickly, and then we'll come back to the elliptical orbits, and we'll solve an example from it that will address two of Nicholas's questions, one that he asked in the previous lecture and one that he asked right now. Okay, so parabolic trajectories, the idea is E eccentricity vector is equal to 1. Okay, what will happen to your equation, the orbit equation, when your eccentricity vector is 1? R is going to be equal to h squared divided by mu, 1 divided by 1 plus cosine of theta. Okay? When theta equals to 0, yeah. What will happen to us when theta is equals to 180? Which means that your R is going to approach infinity. Right? 1 over negative 1. Theta this cosine of 180 is negative 1. 1 over 1 minus 1, right? 1 over 0. Okay? So R is going to approach infinity, which means that, say this is your focus, and you have the P here. This is your apse line. This is how it's going to look like. It will look like a parabola, right? What can we say about the specific energy on a parabolic trajectory? How did we calculate a specific energy? Let me see if we have the equation over there. Oh, I removed it.
E squared over 2 minus 0
P squared over 2 minus P squared, V squared over 2.
V squared over, V squared over 2 minus mu over R.
Okay, that's equal to epsilon. But what can we say about this epsilon? How did we calculate epsilon? It was a function, yes,
Mu over 2a.
mu over 2a. But do you have the equation in terms of R? A is directly related to R, right? That's just, we found that equation in terms of R in the previous lecture, so you don't need to go back that much back. But we already know that A is directly related to R, right? So when R goes to infinity, A also goes to infinity. What does it mean for a specific energy, which is inversely related to epsilon? 0, right? That's it. And then at theta equals to 180, epsilon is 0. We already proved that epsilon is a constant value, which means that the specific energy for all of the parabolic trajectory is 0. We started from a negative specific energy in the circular orbit. Then it became less negative in the elliptical orbit. It was still negative. Then we have moved on to 0, right? Moved up to 0, if you will. Okay. So using this, we can actually find the velocity for a parabolic trajectory, which is going to be equal to 2 mu divided by R. If you recall, the circular velocity was mu divided by R, which means that V of a parabolic trajectory is a square root of 2vc, which is a circular orbit velocity. Okay? But what will happen to our velocity when we go far enough, when R approaches infinity? Velocity. It will approach 0, right? It will become 0. So what does it mean? It means that we have escaped the gravitational pull of M2, but that's it. You can't move anymore. You can't move any further. As soon as you escape the gravitational pull, your kinetic energy becomes, I'm sorry. This person has been calling me 5 times now. Just 1 second. I'm sorry. I'm going to be furious. Okay, where were we? So you have lost all of your energy to escape the gravitational pull, right? Okay? And which essentially means that this is the escape velocity. Right? All of the velocity you need, all of the kinetic energy, if you will, you need to escape the gravitational pull of M2. Okay? And let's see what else we have here. The flight path angle gamma can be calculated as sine of theta divided by 1 plus cosine of theta. We can also prove eventually that your flight path angle in a parabolic trajectory is equal to 1/2 of true anomaly. Okay, there is one bonus point here for you, and you can actually find this in the book as well. Just to make sure you understand it when you're copying it. Prove that this trajectory is hyperbolic. Oh, it is parabolic, I'm sorry. Prove this trajectory. I've lost the track of it. Prove that this trajectory is parabolic. This is parabola. And since I've seen that no one is turning in bonus points anymore, which is all right. But if you don't turn this in, it will be a homework problem. So you can either turn it in and get bonus for it, or just do it as a chore. Okay. I mean, homework. You have to do homework. There's no other way around it. Okay, let's move on to hyperbolic trajectories. We are not gonna stop that much on these, because all of the RPs, all of the RAs, all of those things we can just simply calculate. Hyperbolic trajectories, we're going to have a hyperbolic trajectory when your E becomes larger than 1. Eccentricity larger than 1, hyperbolic trajectory. Okay. So R is equals to h squared divided by mu. This is your orbit equation. And this will be 0 when cosine of theta is equals to -1 over E, right? When that's the case, and that can happen, right? Cosine of theta is equals to 1 over E. At which case, your R is going to approach infinity. In a hyperbolic trajectory, we are going to have 2 asymptotes, right? You're going to approach these lines in infinity. This is your P, F, and then A, F prime. This is your empty focus, the real hyperbolic trajectory. Let's actually make the definitions here. We call this RA. This is your RP. And this is the point P. On an ellipse, point P was on top of the center. This is not point P. Let's call it point, this is point B. This angle here is angle beta. This is angle delta. A lot of different names. So RP, I'm sorry, this was the semi-major axis. This is RA. RA, the semi-major axis, and we also have this length as the semi-minor axis. And let's see what else we have. This is theta infinity. And this is called the aiming radius. So it is obvious from this figure that theta infinity is actually the theta at which you are going to get negative or infinite radius, right? Your radius is going to approach infinity, which means that you can find theta infinity by taking the inverse cosine of -1 over E. That's a true anomaly of the asymptotes. This is called the true anomaly of the asymptote. Whatever, of the asymptote. Beta can be calculated by taking the inverse cosine of positive 1 over V, and delta is 180 degrees minus 2 beta. If you play with that, you're going to end up with sine inverse of 1 over E. I'm pretty sure you know how to calculate RP and RA here. How can we calculate RP and RA? Same equation, right? RP, cosine of theta. -1 is going to give you your RA. Cosine of theta, +1 is going to give you your RP. And 2A, again, here is equals to RA. Plus RP. Just have to be wary of the negative signs, the directions. We also have the equations for A. Let me actually give you the equations for A. The sign is going to be different. A is going to be equals to h squared, 1 divided by e squared minus 1. And your r is equals to a e squared minus 1 divided by 1 plus e cosine of theta. The only thing that remains is the delta. That's the aiming radius. This aiming radius can be calculated as a square root of e squared minus 1, which is essentially the same length as this b, as b in the previous case, and here in the, let's see. Another bonus point is proving this is a hyperbolic trajectory. All of the conditions and whatever you need is in the equation. Prove this is hyperbolic. So to make these, to prove these, you have to have the equation for a parabola and the equation for a hyperbola, right? Then find x and y based on the orbit equations, and you should be good to go. Okay. Yes.
I'm just a little confused. Are the masses on the foci for the? Okay, so it is passing it.
Yes. The masses is always on this non-empty focus. So M1, masses are not on the foci here, just on one of the focus. And M2, that is passing your mass, is here. The same is true here. Okay, so what can we say about the epsilon in this case, the energy in this case? The energy in this case is non-zero, but the difference between the energy of a hyperbolic trajectory and the rest of them is that the hyperbolic trajectory has a positive specific energy, right? Let's write this. Mu divided by 2r is equals to mu divided by 2a. This is your epsilon, or a specific energy of a hyperbolic trajectory, right? Okay. So what does this look like to you? This mu divided by 2r. This is the escape velocity, right? This is similar to the escape velocity. So we can replace this by, let's see. Eventually, if you do the analysis, we are going to get, if you do the simplification, v squared. See, this is v squared divided by 2. Then over here, we're going to get mu divided by a, which is v infinity. Velocity at theta infinity. Okay? So what does this tell you? That this V infinity, whatever velocity you're going to have when you escape the gravitational pull, is equals to your V infinity at any true anomaly minus the escape velocity at that true anomaly, at that R. Okay, V infinity here is actually the hyperbolic excess energy. Okay, yes.
So since it has positive specific energy, is this how you do gravity assist? Since parabolic, you don't leave with any more energy than you came with?
So essentially, the hyperbolic trajectory is the thing you want to have when you are doing the interplanetary missions. For what?
The intergalactic super hot.
Yeah. If you want to build an intergalactic superhighway or whatever, you want to make sure that you have some excess energy, right? So when you're escaping a gravitational pull, you have left. I mean, you have kinetic energy left to get to another planet, right? And then deal with that. Does it make sense? Okay.
So hyperbolic is useful, parabolic is not. That's what I'm getting.
Sometimes you just want to shoot something into space and let it stay there, right? And not move, I guess. But something that you have to keep in mind is that eventually, okay, that's a very interesting. I guess we don't have time to solve the example that would answer your other questions. So let's talk about this question. I love your questions, though. So, I love it. So let's see, in the real solar system, let's see what happens to a satellite that is on a parabolic trajectory. What will happen to it eventually when it escapes the Earth gravitational pull? What do you think will happen? It will get stuck into the sun's gravitation. So it will start orbiting around sun, right? So in real case, if you want something to start orbiting around sun, you want it to have a parabolic trajectory, right? You want to have it. You want it to have a determined orbit. It's essentially the Earth orbit, right? You shoot it out with on a parabolic trajectory, right? But if there was no sun, it was just an Earth and a satellite that's moving. When it moved out of the Earth orbit, it would have had a zero velocity. Okay. And let's see. Let's see what else do we have here. Let me tell this as well. The interplanetary mission energy, V infinity squared, is also called C3, just in case. So whenever I ask you to find C3, this is what you need to find. I assume if you end up working on the Mars mission, this is something you're going to see a lot, hopefully. Actually, we are already working on Mars mission in this university. There are a couple of projects. So you're always welcome to join them. Huh? Where? We are doing some numerical analysis on the Mars mission. How to take the cryogenic field, because you need to. We can talk about it later after the call. I should have said this. I am working on the Mars mission. So mu divided by h, we can also find V infinity, mu divided by h, e sine of theta is equals to, that's the last equation we are going to see from this type of trajectories or orbits. And we are going to solve an example in the next lecture. Okay, let's actually talk about this before moving on. Nicholas asked a question about the difference between apogee and apoapsis. And perigee and periapsis. This was part of the example. I told you that we are going to see this later, but we didn't have the time today. So let's just talk about it. What is it? Who knows what's the difference between these? I mean, they're basically the same thing. Based on what you said, they are essentially the same thing, right? Kind of. The main difference is that apogee and perigee is mentioned about the Earth, right? And the distance from the Earth. So that's the only, that's the main difference. That's actually, if you go back to the origin of these letters here, Epo, I think so, yeah. Epo means around, and G means Earth. So moving around it. That's the closest you move around it. Peri means, no, I said the other way around. Epo means away, right? Peri means around. Yeah, peri means around Earth, away from Earth. It's Greek origins, Latin origins, whatever. So, but this is more general. That's when you're dealing with Earth, you're also dealing with the radius of the Earth. You have to include that in your analysis too, right? Which is, I think, what Igor was trying to get to, right? Okay. So that's it for today. We are going to start by solving an example in the next lecture. And good luck. Have a good weekend.